Could take it outside or to the back of the room, that would be greatly appreciated. And just as a reminder, we have the Qualcomm sponsored break coming up at 3:30 in the foyer. We'll have treats and so forth out there for you. So it's not on the schedule, but it will be happening later on today. And I guess without much further ado, let's welcome Addie Sood to the stage.
Good morning, everyone. I think I'm audible. So today we are going to talk about Malandroid and the crux of Android infection. So this talk relates to the complete study of Android malware from the last year to this particular point of time. It involves some of the research that I have done related to this because I work I do my PhD at Michigan State University. So I do a lot of work related to malware. So that actually fetches my interest in the origination of mobile platforms to try to look at the things and try to build some malware taxonomies that will be pretty easy to understand and then get to the different set of samples. Analyzing Android malware also helps us to build up a typical analysis of the various points when we're doing an application reviews or doing an audit of certain Android apps. So it all works in a pretty way. So let's get it started. Just a little background of mine. I'm a senior practitioner at IOActive and a PhD candidate at Michigan State University. Just a little bit information about my work and where I do present at conferences. All right, so today's agenda, we're going to talk about Android security overview. And we're going to talk about Android malware taxonomy, insidious infections, reversing Android malware, just a one case study, try to look at how the real latest Android malware are working. Then the Chinese alternate markets. So I've been analyzing a lot of other botnets like Inspire, Zeus, and other set of work, so that actually makes me curious. Like, is there some sort of bonding between Android malware and those guys? So we'll take a look at it in some of the connecting dots and apart from the Android malware, what other Chinese guys are doing and try to delve into their alternate market websites. Existing Android events, big problems in Android, and we'll conclude with the message here. So in this talk, we study the interesting tactics in the Android malware from 2011 to until now. The idea why looking at the background is, because in order to understand the real infection, we have to get back to the source, where the things have actually started from, and to build a new benchmarks, a new matrix in order to understand Android malware and what we'll be possibly encountering in the upcoming time. So I just want to spend some quick time over this particular slide. And this actually an overview of the Android existing market. It started with the cupcake and then goes to the jelly bean. The real advancements took place with the gingerbread. And if we look at the different kind of exploit mitigation stuff has been put in, the gingerbread was thwarting the sort of format string vulnerabilities. Then we have another sort of protection in the gingerbread, typically related to hardware-based detection or protection of heap and stack with a non-execute protection. But that was pretty fine. And this statistics usually says us this version of gingerbread is being still running on 55.5 or 50.5% right, Android devices. So the idea is still vulnerable. Why this, even if we had developed for till up to the jelly bean, why still the gingerbread is running? Because of the market, because of the vendors, and because of the existing Android devices that are still running pretty wild. And they're still using this gingerbread version, and they cannot move out of it. And if they do that, there will be a pretty much loss to the business and other sort of things. After that, the real advancement started with the ice cream sandwich, with the thing they started implementing the address space layout randomization for the exploit mitigation. But if you analyze certain version of ice cream sandwich, so the ASLR was not properly implemented at that point of time. But they started implementing protecting the exposure of kernel level addresses by implementing a protection such as dmessage restrict or K pointer restrict structures, or to compile a code with these kind of flags. But with the advent of Jelly Bean, things started really, into growing with the Android market. And they have implemented a lot of different ways. Like if we talk about the address space layout randomization, they talk about 3 different ways. Like first one is the PIE flag, where you want to actually compile your binary. And using the PIE flag is like independent executable. And while you combine your code with this particular flag, you randomize that executable address in the process address space, which actually prevents the return-oriented programming attacks. And with the Gingerbread version, they actually exploited a vulnerability with the Gingerbread exploit, where you actually get a control over the global offset table and get a read-write operations on it. But with Jelly Bean, they actually restrict that, and with the advent of by providing certain other flags in the compiling the ELF headers in the various applications that got compiled on the Jelly Bean. And that was like a relocation flag. When you really compile your binary, or you're going to link your binary, you're going to use relocation that actually sets on the read-only permissions on the global offset table. So that's actually setting up the benchmark. Like, we're still running Gingerbread, but we're still actually developing the ice cream sandwich, and the Jelly Beans is still on the way. It has actually entered in the market. So let's talk a bit about the Android vulnerabilities and exploits. So in this particular slide, I have listed like 9 already known Android exploits in the wild. Out of 8, these are particularly exploited by the malware. As we all know, the primary one is the Ginger one, which actually got the read-write access to the global offset table. Then we have another interesting bug in the Android custom shared memory locator with the HMEM. This also provides remote code access and privilege escalations. And if you look at the bottom, there are certain other vulnerabilities in the WebKit itself that started going to flourish. And that actually gives you code execution with some sort of bugs in like floating point number generation. So the idea is that whatever the exploits that we have already detected or found in the wild are being used by the Android malware. And there are several samples based on that. And let's talk about the Android security pillars at this point of time. This is just like a broad view of Android security pillars here. So first, we're going to have the application sandbox. We're going to have a permission model. We have a bouncer. They implemented like a dynamic-based scrutinization platform for analyzing all the applications that you host on a Google Play Market. Then they have a kernel security. Then they are going to have a kill switch, which actually sends up an asset remove command to just remove your app. But there are certain considerations to this particular security model. They are definitely pretty good considering the normal set of applications, but they somewhat might fail in the consideration when we have an advanced level of Android malware. So let's talk a bit about the Android platform realities. There is a huge improvement with the Jelly Bean. There's no doubt these guys are doing a great job for providing like exploit mitigation strategies. But the built-in design of Android platform is somewhat, raises concern. The Android provenance system relates to the permission model. So any application that you install will give you, okay, I needed that particular set of permissions. But the user doesn't have that option to only allow one particular permission and not to allow the others. So either it is a one permission or the all. So you have to allow all set of permission or nothing. That's a big deal. And if you talk about the data at rest encryption point, it actually started with the beginning of version 3, but before that, there was no proper encryption strategies opted by the Android architecture. And if we talk about a very general scenario, there is no built-in mechanism to prevent social engineering and link verification, though there are like third-party vendors who provide certain apps like antivirus guys, and they provide this kind of portability in their applications to actually scrutinize these kind of things. So another big problem is the alternate markets in the Android. We're going to take a look at the repackaging and masquerading just a little later on. But these are certain the realities of the Android platform. Though we are really developing and making it like, not prone to exploits, but these kind of things, the default design, the design behavior, really allows a lot of things to be executed by the malware authors. So before actually talking about the Android malware, I always prefer to talk about the malware taxonomy. And the malware taxonomy actually helps us to understand what kind of different layers we are targeting in this particular set of Android malware and help us to classify different Android versions. So I found like there is some other researcher from the North Carolina State University. Those guys have done a great job in building up a malware taxonomy too. But what I did, like I built very generic ones. So if you guys gonna look at it, and you will find that it's pretty easy to understand. And let's take a look at it. So if you talk about the type S malware, we used to call a standalone. And talking about the the architecture of Android here, we have an application framework, libraries. At the bottom, we have a Linux kernel, and then a hardware emulator. Any app that just simply install as a standalone in the Android device and don't do anything typically, and just only look for the users to interact with it and then push your credentials somewhere back to the command and control servers. It's typically an example of standalone malware. And it started, if I remember, it started with the fake Netflix application. So some of the malware authors simply put that in the alternate. And I think maybe in the legitimate Android market and you download it, it looks like a legitimate Netflix app, but do the things for you. Now let's talk about the Taipei application layer malware. So this kind of malware actually exploits the application functionalities in the Android architecture. So it can interact with different kind of applications that are running inside the Android device. And for example, talk about the exposure of different activities, different services, typically about the malicious intents. So the one app can send up a malicious intent to the another if they have a particularly exposed features or the particularly exposed permissions in that. And it definitely impacts the component model. And it has then this kind of layer. So this actually gives you the malware, which is in a type A, the application layer. And of course, if you're talking about any architecture, we have to get back to the kernel layer. And this is the call as in a type K malware, which actually exploits the inherited functionality of the Linux kernel that is actually present at the bottom of the Android architecture. So it can be anything. It can be malicious Linux kernel modules, native exploit codes that can be fetched from the remote resource and actually run the native code to exploit the integrity of Linux kernel at the bottom. So we talk about like type S, type A, and type K. That actually gives us, whenever we are going to analyze a particular set of malware, we say what kind of characteristic that malware has, and then we can really get into, okay, if this is a malware, it's gonna do only that kind of thing. So what next? And the next one is the hybrid one, which is being, I think, like from the last year, the Chinese malware authors are really writing the great hybrid malware, which actually constitutes a lot of functionality from different layers. So it can be a standalone app. It can be an app that actually communicates with the other app. And it can download a native code from the remote execution, and then it can exploit the kernel too. So this design is actually being opted by the Android botnets. And all the Android botnets are typically a hybrid in nature if they have a large set of functionalities, if we talk about. So if we talk about like a SMS-based botnet malware, it might not be a hybrid because it is not even required for that particular kind of malware to actually exploit or root the phone. But that is there. So this actually gives us an idea that how the Android malware taxonomy actually works. So what matters in the Android malware field? Malware hosting. Where the malware is actually hosted is like the legitimate Android market or the alternate Android markets. Delivery model, where it matters a lot, like you're hosting your code on websites, you're using a phishing, and then sending it within attachments, drive-by downloads, malicious attachments. And the state of devices, whether the Android phones are rooted or not, and then there is unrooted Android phones. Talk about the exploitation level. We have a remote exploits from the root servers. I mean, because Android provides the code execution at the native level, the app can fetch the code, which actually does not run in the Dalvik virtual machine, but actually executes on the native level to exploit the kernel. And the threats are definitely there: information leakage, online banking frauds and thefts, targeted attacks, Android botnets, and pivot attacks. If we talk about like a little about the pivot attacks, it's like against the GSM networks and subscribers, but these are the firmware based. The firmware has to be infected to perform some sort of eavesdropping if we really want to execute pivot attacks. But this will be the future. Some of the things have been seen, but in the coming time, these kind of attacks will be launched against like corporate networks if we don't cure what is going on in the Android malware field. So let's talk about insidious infections and design strategies. And the overall component with this particular deck of slides, which I'm going to talk about, is like can be used while you are doing an auditing of Android apps and a lot of other things. I think all these things should be looked upon even if you are analyzing malware or even if you are going and auditing any apps. So let's take a look at the last year most classics malware. Started with Droid Kung Fu, Root Smart, Gold Dream, Hippo SMS, and all those sort of things. There are many bots, the N-Server bot, Bean bot, which are being designed by the Chinese malware authors. Well, it started within, I think, in the start of the 2011, but the design still keep on stretching. And if we look at this particular slide, and it gives you the latest in last few months. Fake Lookout, Plankton variants, Finfisher, Loose Fawn, a Japanese Android malware, we in a find and call, MM Marketplace. And this particular malware call is like MM Marketplace. It actually utilizes your the kind of money you have in your Android phone to send spam messages and a lot of other things which cost you something. So what my point is here, the Android malware started infecting from the last year in 2011, but still it's growing really wild. And in the later on these slides, we are going to connect some interesting dots with the Android platform that are being exploited by the Chinese malware guys and a lot of other things. So let's start with the application masquerading. This is a very interesting technique and the most generic one in the field of Android malware. I think like approximately 80% of the Android malware that have been analyzed previously uses this application masquerading. The simple process is this way, like a legitimate developer actually writes the application, develops the application, compile it, puts a SysOn signature over it, and hosts it on the Google Play legitimate Android market. And then the malware author comes and see that, okay, hey, this particular application is getting a lot of traffic. So what can I do with it? He downloads the app, and then opens it, repackages it, and puts something malicious code inside it, and then start distributing on the alternate markets. That's a very simple model of repackaging which we used to call application masquerading. So since all the applications runs inside a SON model, but application has a lot of capability in Android architecture, as I stated earlier, code execution, fetching of remote exploits, and sort of things. So the application looks legitimate, but there's a Trojan in the back end that actually do a lot of stuff for you. And that particular Trojan can check a lot of options in your Android phone too. This is a very interesting part which I analyzed while analyzing a lot of Android malware. There's like stealthy assets. The stealthy assets are like somewhat different from the raw resources that you put in Android. Like for example, developers are developing some sort of application and they want to write some assets for it. And while you're writing an assets, you can disclose a lot of application path in it. You can obfuscate some of the things, or you can put some of the application functionalities in that assets, which you will dynamically bind when you call your application. And in order to do that, there is an asset manager.list which dynamically calls the assets. But these assets are different from the resource raw, which is another set of directory that a developer actually uses. So the difference between assets and the resource raw structure is that assets can be called dynamically. Assets can be set up as in a hierarchy, is a tree layout. So there isn't a path from the root directory to the third level directly. They can call it directly. And so they don't need to have an identifier for that. But with resource raw structures, they need to have identifier. And the assets do not require identifier, as I stated earlier. So it becomes really easy for the guys. Like they can put something code in the assets, hide it, and then call it at the dynamic runtime to make the things work. So it was analyzed like malicious PNG files were used for that. Like they actually put the APK files and then change the extension and then actually dynamically fetch that PNG file during runtime, looks for the assets, and get the things done. So stealthy assets is a really bad approach that most of the malware authors are using to hide some of the interesting functionality or the components of Android malware. Now, bootstrapping payloads and services. This kind of functionality is been known for a little time, but it actually provides you a lot of control over the Android infections if you really want to do that. The idea is simple. Any repackaged app has some sort of built-in code that actually checks for the Android intent action boot completed. Very simple. Okay, if the device has successfully booted, send me a notification, send me an intent, and I want to perform some malicious activity on the device. So what else can be done is like registering a malicious service. It's pretty interesting. Like you download an app, it remains dormant, it's not doing anything, it's wait for the device to get rebooted and gets a notification back from the system, then registers a service that actually monitors Android phone and extracts like a lot of interesting information from your device. And typically this design, bootstrapping payloads are used for installing services, the hidden services at the backend. Let's take a look at the Android bootkits, an overview. Not very much number of samples have been seen in the wild about Android bootkits, but there are like a DKF bootkit, which actually use a lot of interesting functionality by manipulating the boot scripts and other things. So as I stated earlier, 80% of the apps are repackaged. Again, the infection starts, okay, download another app from the alternate market, which has some sort of Trojan built inside it. And how that things work later on, registering agent controller service. So whenever the particular application, the legitimate application, which has some masqueraded code in it, is downloaded and executes, it typically looks for certain permissions. And for the perspective of Android bootkit, it has to install and activate a boot sequence manipulation agent. Because bootkits, what it actually means that as soon as you are booting, let's make some modifications in the boot scripts that actually gives you the system level access, or to execute some code which requires system level access. And to do that, it really requires the boot sequence manipulation agent. And the BSM agent validates first whether you have a root privileges. If you do, then it's going to mount a system folder somewhere and then gets the read-write access to it. Once it do that, after that, the infection process starts and going to manipulate, because since it has a write capabilities, it's going to manipulate the booting scripts and a lot of other things. Typically used for hijacking Android framework at the boot time. Now let's talk about the custom firmware images. I think this is another install, but this kind of exploitation really requires the firmwares to be distributed on the internet, maybe in the underground community or maybe the third-party application providers. But with firmware exploitation, you have to really build the code while you're compiling. I mean, you cannot do a dynamic firmware upgrade. It's pretty hard. So that's why when you build a malware-driven firmware, it has to be installed on the device. And sincerely asking me on that part, I found that like users don't give a damn about like what they are actually doing with Android. Very few users are really concerned or paranoid about Android malware, which we'll take a look later on when we're concluding something. So with custom firmware images, you can enhance the stock ROMs, which we used to call read-only memories on that particular one. And while you have to enhance it, it is like stock ROMs which are already installed on the devices. You might want to manipulate it. Then you can also use the Android open source project to build up and then sign up those firmware. Another interesting trick is like, I haven't seen much in the wild, but this is always there. This can be done. Like let's talk about two different attacks that can be done in the firmware by exploiting the integrity. First one, if you have a third-party firmware, you can simply put up a TCP open port connections and setting up with the set prop, or you can simply set up in these parameters in the file, in the RAM disk, and recompile it. So whenever that firmware gets activated on the device, it will simply sponsor you a shell on TCP, particular port. Another interesting thing is that you can configure build.prop to tweak the ro.secure parameter, and as soon as the system or as soon as the user boots up Android device, it gives you the user level access. But the big problem with custom firmware images is that if there is some problem occurs with tweaking, it can simply make your Android firmware to go haywire, or it can really, impact the stability of your Android device. We'll look at some of the interesting facts of like Insidious infections, but how they are going to defend the code. This is a very interesting part. When we look at the system level malware, like Windows-based malware, there is a lot of obfuscation and encryption. But the similar techniques are also being started deployed by the Android malware in the recent times. The very first, we are going to take a look at the code. If you're writing code, do obfuscation, do encryption. Simply, obfuscate the class names that are not easy to decipher when any analyst is going to analyze it. That actually makes the invocation process a bit more stealthier. I mean, when you're analyzing, disassembling the code, and you say, like, this particular class is calling this particular method, so where is the relation? Where is the interdependency among them? And with the obfuscation and encryption in the Java code, it can make really hard for that. And the network level, of course, we are going to do encryption with the post request. And majority of the malware, if you have what I have analyzed and what I've seen in the last year, they simply use the HTTP-based communication model. Simply send up a GET request with certain patterns, and then you can get the data what you want, or you can exfiltrate the data from the Android device. But that is the case here. It can use post-wait communication, and it has seen by some of the Chinese malware, like Android malware. Those guys have started using this kind of capabilities. Anti-repackaging check is a pretty interesting thing. I mean, so the malware authors repackage the code itself, but they can also use this functionality of repackaging and then check a particular module or a particular component that is embedded in the legitimate app before installing and activating in the Android device. That actually allows the malware authors to understand that particular payload has not been tweaked by the analyst or has not been controlled by the analyst. So there is an anti-repackaging check too. Antivirus detection is easy considering the default model of the Android. So they can install a service at the backend and monitors different processes, and then can really remove the processes that are related to the antivirus. And these kind of capabilities are not being shown by a standard Android malware, which is being used, what I talk about, like a spy agent or spy application hosted on legitimate app. These are primarily on the advanced level of Android botnets. So here I'm going to talk about the time-based code execution. This is a very interesting technique that really impacts the state of Android malware. So if we really remember, within the old days of Windows 2000 operating system and XP, we used to write time bombs using a Windows scheduler service. Okay, if there is a 12 p.m., execute this particular code. So I can map this particular same functionality to that kind of thing. I mean, in the Android world, you can base a time-based code execution. So what happens, you actually write an application, and you have to download a malicious payload from the third-party server, right? So in order to do that, you simply put up, okay, I don't want to download that particular payload at this particular period of time, wait for certain seconds or certain minutes, and then downloads it. And this approaches are being used, I think, can be easily used to bypass the dynamic-based code detection solutions, where they are going to look for the malware and the bit of network traffic, and where the data is exfiltrating, and the external connection that malicious Android application is making. And this is a very, very, very interesting technique, and it's it's not that easy to circumvent it, because timers can be used at any point of time in the code, and that is being required by the developers too. But that is there, and I think even with the bouncer, I mean, that is basically actually looks for the dynamic analysis, and these kind of techniques can be used in that. Now let's talk about the exploiting administration APIs. I mean, this is the functionality has been provided by the Android guys for the organizational level implementation of Android devices. Typically a centralized management solution. Okay, you are using Android device in your organization, and the administrator has to actually enforce a particular set of policies on it, right? They can use that device administration API. And in the recent times, it has been seen that some of the Android level malware from the alternate markets has started using this kind of thing, the administration APIs. Because if they get an access to that, they simply get a direct access as a system level privilege to certain functionalities. And that can be very, very disastrous from that point of view, from the, actually putting up an infection kind of components in the Android devices. And, but this is also a pretty interesting technique. So if you look at this point of time, all